High-ranking military officials now admit 3I Atlas may not be what it seems, but something far more terrifying.
A new look at the interstellar visitor 3I Atlas has revealed something genuinely odd. Sunlight around this object behaves unlike anything astronomers have recorded before, and the comet itself keeps defying expectations. From a faint glimpse in the Martian sky to unprecedented light polarization, 3I Atlas is challenging our ideas about how comets form, evolve, and move through space. A faint Martian glimpse. The clearest early sign of 3I Atlas came from NASA's Perseverance rover on Mars. Using its Mastcam Z camera, the rover captured a faint, blurry patch where the interstellar object was predicted to be. In the image, the comet appears as a small smudge beside stars, roughly around magnitude 8. Barely visible, but exactly where astronomers expected. The shot was taken one day before the comet's closest pass by Mars, a moment best observed by orbiters. Because of agency shutdown complications, detailed orbital images may take time to be released, but the rover's view still matters. It confirms the object's position and behavior from an unusual vantage point, another planet's surface. Perseverance also recorded heightened surface activity at the same time. Dust devils near the rover and a growing dust storm on the horizon. Even so, the comet's tail was too faint to register clearly in those frames. That matched earlier reports that 3I Atlas behaved strangely for a comet, displaying little or no obvious tail. As it neared Mars, however, it began to grow a thin, narrow tail, still much dimmer and tighter than those of ordinary comets. Unverified images taken by other observers hint that 3I Atlas is elongated, making it look more like the first known interstellar object, 1I oumuamua, than the second, 2I Borisov. If confirmed, that shape would be another clue that this visitor doesn't follow the familiar template of solar system comets. It might be a long, tumbling body or a complex aggregate shedding dust unevenly as sunlight heats it. Close pass and disappearance. On October 3rd, 3I Atlas passed within about 0.19 astronomical units of Mars, roughly 28 million kilometers, and raced onward at nearly 200,000 miles per hour toward its closest approach to the Sun, the perihelion. Then the situation changed abruptly. Astronomers suspect a coronal mass ejection. A violent burst of solar particles swept past, after which the comet effectively vanished from ground-based view. Its increasing distance, the Sun's glare, and Earth's changing geometry, moving the opposite way relative to the comet, all combined to hide it against the bright background. Observers expect it to reappear later in the year once viewing angles improve. That brief visibility window still raised a key puzzle. Many interstellar and long-period comets show gentle, non-gravitational nudges from jets of sublimating gas, which act like tiny thrusters and measurably alter their paths. 3I Atlas has been visibly. There is a gas and dust coma around it, yet its trajectory shows little or no deviation that can be clearly attributed to jets. If the object is shedding gas without being pushed off course, the simplest explanation is that it is unusually massive and dense. So small forces have little effect. Early estimates suggested it could be roughly 1,000 times more massive than a typical comet. More recent figures place it above 33 billion tons. If even partly correct, that is immense for a natural comet and raises basic questions. How did such a massive body get ejected into interstellar space? And how common can such objects be? Light that behaves oddly. The most striking results so far come from polarimetric observations, measurements of how sunlight's waves align after scattering off the dust and ice around the comet. When light hits tiny particles, it doesn't just reflect like a mirror. It scatters in many directions, and the waves can become organized or polarized. The amount and direction of that polarization reveal the dust properties: grain size, shape, roughness, and composition, icy, rocky, or a mix. In solar system comets, astronomers usually see positive polarization at larger phase angles and negative polarization at small phase angles. 3I/ATLAS fits the broad pattern, but with an extreme twist. It shows extraordinarily strong negative polarization, far stronger than any comet measured to date. The minimum recorded value, about minus 2.77% at a phase angle near 6.4 degrees, is unprecedented. That implies dust grains very different from those in familiar comets, perhaps rougher, more irregular, more porous, or made of unusual materials. It could also indicate a unique size distribution of grains, with many particles at the right scale to polarize light in this atypical way. This is the first time such behavior has been seen so clearly in an interstellar object. The simplest reading is that 3I/ATLAS formed under conditions unlike those in the zones that build our comets. It might have originated in a colder, more distant environment, perhaps at the frontier of a star's planetary system, where exotic ices form and dust grows differently, or in a region of the galaxy with distinct chemical histories. Some researchers even propose that the object predates our solar system, having traveled from the inner regions of the Milky Way. If so, we are watching an ancient survivor from long before the sun took shape. Origins and open questions. Chemically, 3I Atlas also looks strange. Observers report an environment around the object that, in some respects, resembles Martian atmospheric and surface conditions. If that holds up, it argues against a classic cometary origin and hints that this body, or at least the material now sublimating from it, might come from a planetary crust or regolith rather than a primordial ice reservoir. In other words, some portion of 3I/ATLAS could be processed rock and dust, blasted off a planetary surface in another system, later frozen and carried away, and only now releasing gases and fine grains as sunlight warms it. There are additional curiosities. Some detectors note unusual glow patterns near the object, consistent with a body that could shed mass rapidly or even fragment as it approaches perihelion. The comet has already lost material, yet its path remains stubbornly gravitational, reinforcing the idea of substantial mass or a geometry of jets that cancel each other out. If the nucleus is both elongated and heavy, gas may escape primarily from regions that produce little net thrust, masking the usual accelerations astronomers look for. To bring order to the growing list of anomalies, astrophysicist Aviloeb has grouped them into two piles. The first includes features that might be explained with better data: its true size, the nature of its anti-tail, a forward-pointing streamer of scattered sunlight that appears roughly 10 times longer than it is wide, its unusual chemistry, and the exceptional negative polarization. These could become less mysterious as better images, spectra, and models arrive. The second pile would remain puzzling even with more data. Here, the comet's trajectory stands out. It is aligned within about 5 degrees of the ecliptic plane, the flat plane in which the planets orbit the sun. On top of that, its arrival seems exquisitely timed to pass close to Mars, Venus, and Jupiter in quick succession. Finally, the direction from which 3I/ATLAS entered the inner solar system lies within roughly 9 degrees of the famous WOW signal detected on August 15, 1977. A radio burst once speculated to be of extraterrestrial origin. None of these alignments prove anything extraordinary, but taken together, they are unusual enough that, as Loeb argues, anyone insisting on a purely natural, ordinary comet explanation should be able to show how all these coincidences arise without special pleading. For now, the most conservative stance is also the most exciting. 3I/ATLAS is likely natural, but it is not ordinary. Its dust polarizes light in a way no comet has shown before. Its tail is thin, its shape probably elongated, and its mass may be enormous for a comet. It sheds gas without obvious non-gravitational kicks. Its chemistry may resemble processed planetary material, and its sky path and timing keep inviting questions. Each of these threads points to the same conclusion. Interstellar visitors carry the fingerprints of the worlds and disks that made them, and those fingerprints can be utterly different from the ones we know. As the comet moves toward and then past perihelion, better geometry and darker skies should make follow-up observations possible. When orbiters and large telescopes release higher resolution images and more complete spectra, we'll learn whether the elongated silhouette is real, whether the anti-tail is dust or viewing geometry, and how the dust grains produce such extreme negative polarization. We may discover that 3I/ATLAS is a dense shard of a long-lost world, or a chemically exotic outgassing body from a cold, distant nursery. Or we may find still stranger answers that expand the very definition of a comet. Whatever the outcome, 3I/ATLAS has already done something rare. It has forced us to look again at how light scatters from dust, how comets move, and where such objects can come from. It has reminded us that our solar system's rules are not the galaxy's rules. And it has shown that even a faint smudge in a Martian sky can upend comfortable ideas and open a fresh chapter in the story of interstellar wanderers. Thanks for watching. Don't forget to subscribe to Epic Dive for more amazing documentaries.